Every ounce of it has been treasured by nearly every civilization in human history. Wars have been fought over it. Empires have risen and fallen chasing it. And yet, remarkably, all of the gold ever mined in the entire history of the world, every ring, every coin, every gold bar sitting in every vault on Earth, would fit inside a single cube only about 22 meters on a side. That's it. The rarest, most desired metal in human history could fit in a modest office building. But gold isn't just rare, it's strange. It's one of the only metals on the periodic table that isn't silver or gray. It practically never corrodes, tarnishes, or rusts, even after thousands of years buried in the ground. So where does it come from? And how does a dull, dusty rock become a gleaming, untarnishable treasure? Today we're finding out exactly how gold is made. Gold has captivated humans for at least 6,000 years. The ancient Egyptians were likely the first civilization to mine and work it on a massive scale, as early as 3,100 BC. They pulled gold from riverbeds and dug it from veins in the eastern desert, prizing it so highly they called it the flesh of the gods, believing its untarnishable shine reflected the eternal nature of the divine. Pharaohs were buried in it, temples were covered in it. Centuries later, gold would spark some of the largest human migrations in history. When gold was discovered at Sutter's Mill in California in 1848, word spread so fast that within a year, hundreds of thousands of people had rushed to the American West, gambling everything on the chance to strike it rich. The California gold rush reshaped an entire country, and it all starts the same way it did 6,000 years ago, by finding gold in the ground. Before we mine it, it's worth understanding just how unusual gold actually is. On the periodic table, gold sits among a small family of elements called noble metals. Metals so chemically stable that they almost refuse to react with anything around them, including the oxygen in the air. That's the secret behind gold's legendary resistance to tarnish. While iron rusts and silver darkens, a gold coin pulled from a 2,000-year-old shipwreck can still gleam like the day it was made. Gold is also remarkably dense and incredibly soft as metals go. A single gram can be hammered into a sheet almost a square meter in size, thin enough to see through. That combination of rarity, permanence, and workability is exactly why humans have valued it above nearly everything else. But first, it has to be found. And that search starts deep in the Earth's crust. Gold occurs naturally in two main forms. Placer gold has already been eroded out of rock by rivers and streams over thousands of years, settling as flakes and nuggets in sand and gravel. The kind of gold that prospectors famously pan for by swirling sediment in a pan until the heavier gold sinks to the bottom. But the vast majority of the world's gold today comes from lode deposits. Gold still locked inside solid rock, usually mixed invisibly through quartz veins deep underground. To reach it, mining companies dig enormous open pits, sometimes over a kilometer wide and hundreds of meters deep, using massive excavators and haul trucks to remove huge volumes of ore. Here's the astonishing part. A typical ton of ore, that's about as much rock as a small car weighs, might contain only a few grams of actual gold. Everything else is discarded rock. Mining gold means moving mountains just to find a handful of treasure. Once the gold-bearing ore is hauled out of the pit, it doesn't look like treasure at all. It looks like ordinary rock. The gold inside is often invisible to the naked eye, microscopic flecks locked within the mineral structure. To free it, the ore is fed into massive crushers in grinding mills that pulverize the rock down into a fine powder, sometimes as fine as flour. This dramatically increases the surface area of the material, exposing as much of the trapped gold as possible. The crushed ore is then mixed with water to create a slurry, a thick, gray, gritty soup with gold hidden invisibly inside it. At this stage, there's still no glint, no shine, nothing that looks remotely precious. The gold has to be chemically coaxed out, and that's done with a surprising and controversial ingredient. The most common method for extracting gold from crushed ore is called cyanide leaching. The powdered ore is piled onto massive collection pads, sometimes covering areas as large as several football fields, and a dilute cyanide solution is sprayed continuously over the top. As the solution trickles down through the pile over days or weeks, the cyanide chemically binds with the gold, dissolving it out of the rock and carrying it downward as a gold-bearing liquid, which is collected at the bottom. This single process handles the vast majority of gold ore processed worldwide. From there, the gold-laden solution is treated with fine carbon or zinc dust, which causes the dissolved gold to bond and drop out of the liquid as a solid once again. What began as dull gray rock has now become a crude, impure lump of gold, and it's ready for its final transformation. The recovered gold material is still far from pure, mixed with silver, copper, and other trace metals. To consolidate it, it's melted down in a furnace at temperatures over 1,000 degrees Celsius, along with fluxing agents that help separate remaining impurities into a floating layer of slag, which is skimmed away. What remains is poured into molds, cooling into rough, dull-colored bars known as doré bars, typically somewhere between 60 and 90% pure gold. It's a far cry from a gleaming gold bar in a vault, but it's an enormous leap from where the process started. These doré bars are then shipped to specialized refineries, where two remarkable chemical processes will push that purity to nearly perfect. The first refining step is called the Miller process, patented in 1867. The impure doré bars are melted down once again, and chlorine gas is bubbled directly through the molten metal. Here's the elegant trick. Nearly every impurity in the mix, metals like silver, copper, and zinc, reacts eagerly with the chlorine gas, forming chlorides that either float to the surface as a removable slag or escape as a vapor. Gold, true to its noble nature, does almost nothing. It simply refuses to react, sitting inert in the melt while the chlorine strips away everything around it. Within about an hour, this process can push gold purity up to about 99.5%. That's remarkably pure enough for many commercial uses. But if you want gold pure enough for investment-grade bars, there's one more step, and it involves electricity. For the highest purity gold in the world, refineries use a process called electrolysis, developed in 1874. A bar of the 99.5% pure gold is submerged in a chemical bath and used as an electrode, with an electric current run through the solution. As the current flows, gold atoms dissolve off the impure bar and travel through the solution, redepositing themselves, atom by atom, onto a separate strip of pure gold. Because of gold's unique chemistry, it separates from the remaining trace impurities with incredible precision. The impurities are left behind in the solution or as sludge, while pure gold steadily accumulates, crystal by crystal, on the receiving electrode. This process can push gold purity above 99.99%, the standard for investment bars and the finest jewelry. From a truckload of ordinary rock, humans have engineered something as close to chemically perfect as metal gets. Here's something remarkable that most people never learn. The very reason gold is yellow, and the very reason it never tarnishes, come from the exact same piece of physics. Gold atoms are unusually heavy, and their innermost electrons orbit the nucleus so fast that they begin to experience effects predicted by Einstein's theory of relativity. Their mass effectively increases, pulling them into tighter, more contracted orbits than normal chemistry would predict. This relativistic squeeze changes how gold's outer electrons absorb light, shifting its absorption toward blue and violet wavelengths, and reflecting back the golden yellow we see. That same relativistic effect also makes gold's electrons unusually reluctant to react with oxygen, which is exactly why gold resists corrosion so well. In other words, gold's beautiful color and its legendary permanence are two sides of the very same relativistic coin, a genuine quirk of physics baked into every atom. With pure gold finally in hand, it's ready to become something beautiful. Refined gold is melted once more and cast into ingots, coins, or wire, or handed to a goldsmith to become jewelry. Because gold is so soft in its pure form, it's often alloyed with small amounts of other metals like copper or silver to increase its strength and durability. This is where carat ratings come from, describing what fraction of the metal is actually pure gold. A skilled goldsmith works this alloy with remarkable precision, heating it with a torch to make it malleable, hammering and shaping it into rings and settings, soldering delicate joints, and setting gemstones by hand. Gold's extraordinary malleability, the same property that let ancient Egyptians beat it into paper-thin gold leaf, is what allows modern jewelers to coax it into impossibly fine and intricate designs, one careful motion at a time. While most refined gold ends up as jewelry or investment bars, a surprising amount is quietly at work all around you. Gold is an outstanding conductor of electricity, and once again, its resistance to corrosion means those electrical connections stay reliable for decades without degrading. That's why gold is used to plate the contacts inside smartphones, computers, and countless electronics, including, as we covered in an earlier video, the connectors on circuit boards. Gold also reflects infrared radiation exceptionally well, which is why astronaut visors and satellite components are often coated in a microscopically thin layer of it, shielding against the sun's intense heat in space. From the depths of a mine to the vacuum of orbit, gold's rare mix of properties keeps finding new jobs, thousands of years after it was first pulled from a riverbed. Before we finish, here are a few facts to marvel at. All the gold ever mined in human history amounts to roughly 219,000 tons. And remember, that's small enough to fit in a cube barely 22 meters wide. Gold is so malleable that a single ounce can be hammered into a sheet covering more than 180 square feet, thin enough for light to pass through. And because gold never degrades, virtually every ounce ever mined still exists somewhere today. The ring on your finger might contain atoms once worn by an ancient pharaoh. Unlike nearly everything else humans dig out of the ground, gold is never really used up. It just keeps changing hands, generation after generation, exactly as valuable and untarnished as the day it was found. From a dull gray rock hauled out of an open pit to a gleaming, untarnishable treasure shaped by hand, gold's journey is unlike any other metal on Earth. It's rare, it's strange, and thanks to a quirk of relativistic physics, it may be the closest thing to eternal that we can hold in our hands. If you enjoyed this video, subscribe. We break down how everyday things are made every single week. And leave a comment below. What should we melt down and explore next? Thanks for watching, and we'll see you in the next one.